Hello everyone, let's analyze. So in our last lecture, we used the definition of the derivative to prove several familiar derivative rules. The product rule, the exponent rule, the quotient rule, and today we'll prove the chain rule. Now, given our previous approach, it's tempting to assume that when we apply our limit to our secant slope function of some composite function g of f of x, that we would be able to just split that fraction into g of f of x minus g of f of x naught over f of x minus f of x naught. This would be the df in the denominator and a df in the numerator, divided by x minus x naught. And that we just take the limit of that as x goes to x naught. And if this was your inclination, if this is what you thought we would do, well, then you're almost right. In fact, this is actually the main idea behind the proof, but there are some subtleties that we need to be careful about. Specifically, it's possible that f of x minus f of x naught is equal to 0, even if x is not equal to x naught. And this leads to problems showing that the definition of limit is actually satisfied. But we can essentially get around it by making the secant slope function explicitly continuous for the function g at f of x naught. So we have to take some subtle side steps, but taking this limit is the main idea of what we're going to do. In fact, this is why it's useful to remember the chain rule of the composition of g and f as dg df times df dx. So let's give a statement of the chain rule. Suppose f maps d to r and g maps d prime to r. The image of f is inside the domain of g. Now, of course, that has to happen because we're composing g and f. In other words, x gets warped by f of x gets warped or operated on by g. Right? We're considering function g of f of x. Whatever f outputs has to be a feasible input to g. If f is differentiable at x naught and g is differentiable at f of x naught, then the composition of g with f is differentiable at x naught, and its derivative is g prime evaluated at f of x naught times f prime of x naught. So let's prove the statement. All right, so our goal is to show that the secant slope function has a limit at x naught. Remember, that's what the derivative is. It's the limit of the secant slope function as the width of the secant goes to 0. When it goes to 0, you get the slope of the tangent line instead of a secant line. Okay, so what do we know? Okay, we know f is differentiable at x naught, which means x naught is an accumulation point because differentiable means a limit exists at x naught. So if you define the secant slope function, t, we'll add a subscript f to just denote that it's the secant slope function for f. We get f of x minus f of x naught over x minus x naught. That's rise over run of our secant. We know that the limit of this secant slope function exists as x approaches x naught, and it's specifically equal to f prime of x naught by definition. Now we also know that f is continuous at x naught from our last lecture, where we showed that differentiability at a point implies continuity at a point. Now we also know that g is differentiable at f of x naught. Now x naught is a particular number, and f of x naught is a particular number in the domain of g. So when we see f of x naught, we shouldn't think a function, we should think of a number, right? It's just some number in the domain of g, d prime. And that number, f of x naught, that number is an accumulation point of d prime because g is differentiable at that point. Typically, secant slope functions are undefined at the point that you take a limit on account of the fact that you got to divide by 0, right? Even if that limit exists. So we're going to explicitly make the secant slope not only defined, but also continuous. So let's define for y in the domain of g the secant slope function tg of y, which when y is not f of x naught is our standard secant slope function. But when y equals f of x naught, we get g prime of f of x naught. Of course, we know that number exists, and specifically, this number is the limit of this secant slope function as y approaches f of x naught. We know that limit exists because the limit of the secant slope function is the derivative of g at f of x naught, which we know it exists. So these are all things we know just from the hypothesis of the theorem. So, as we said, as y approaches f of x naught, tg of y is g prime of f of x naught, which, by the way we constructed this particular secant slope function, we said that is tg of f of x naught. That means when we couple this fact with the fact that f of x naught is an accumulation point of the domain of g, that tg of y is a continuous function at the value f of x naught, which remember is just a number in d prime. So from our results about compositions of continuous functions, we can also conclude that the composition of tg and f of x, remember tg is the secant slope function of g, composed with f, means we're going to take the secant slope function of g and evaluate at f of x. We know that it's continuous at x naught. Well, because f is continuous at x naught by the fact that it's differentiable, and tg is continuous at x naught because we essentially added the value to the point where the limit exists. That means we can take the limit as x approaches x naught, and we would get, because we have the composition of two continuous functions and we get another continuous functions, we get t composed at f at x naught, which is tg of f of x naught, which from here is g prime of f of x naught. So now, as we've kind of cataloged what we know, we actually have come to a point where we can take the limit of our goal secant slope function. Remember, the definition of the derivative of g composed with f at x naught is the limit as x approaches x naught of rise over run of a secant. Well, that's equal to the secant slope function of g evaluated at f times the secant slope function of f evaluated at x. Which, by the way, this product here is almost the bad idea that we started out with. Essentially, this. The secant slope function of g evaluated at f of x and f of x naught. That's essentially what we have here. Except that we made it continuous at the point that y equals, or f of x equals f of x naught. So because the limit of this and this exists, I can distribute the limit into my product. We know what this is equal to. We've already computed. It's g prime of f of x naught. And we know what this is equal to, right? The limit of the secant slope of f is f prime, right? That's the definition of the derivative, and we know it exists. And, well, we have our chain rule. So now let us reap some of the benefits of the chain rule. Let's consider the exponential function b to the x, where b is some positive number. Euler's constant E can be defined in a number of ways, but one way is that it is the exponential function base, right? It's the base b that has a tangent slope of 1 at x not equals 0. Now we can use this fact to compute the derivative of, well, all exponential functions everywhere. Let's start with the exponential function with e as the base. Let's let f of x equal e to the x. Then f prime of x, if it exists, equals the limit as h approaches 0. We're taking the perturbation secant slope function of e to the x plus h minus e to the x over h. H is your run. E to the x plus h minus e to the x, that's your rise. From the numerator, I can factor out e to the x, and I can take it out of the limit because, well, there's no h involved. And notice that my limit is essentially the derivative at 0. And the derivative at 0 is the slope of the tangent line when x is equal to 0. Now, we said that by the very definition of e, that's 1. So f prime of 0 equals 1 by definition of e. E is the particular exponential base that happens to cross the y-axis at a 45-degree angle. Now, of course, we are bypassing some of the details. For example, showing that the limit of e to the x at 0 exists rigorously for any base. But that's not the subject of this lecture. We just want to get on to our shiny exponential toy and cool chain rule accessory. So let our base b be positive and consider the exponential function g of x equals b to the x. Let's also define the inverse of the exponential function, the log base b function. When I say it's the inverse, that means if log b maps x to y, then b to the y is equal to x. Essentially, we could think of log b of x as a question. Log b of x means what power of b is equal to x? Well, certainly b raised to that power is x. In other words, b to the log b of x, which remember is the power of b that equals x, well, b to that power is x. That's the statement here. Of course, that's a composition of functions. That's the composition of g, the exponential function, composed with the logarithmic function, base b. So we see that they're inverses because when I apply that to x, I get x. Of course, similarly, the composition of log b with g, in other words, if I reverse the order and apply it to y, I get y. You might look at that and say, that's not y. Well, that's because that's a typo. Forgive me. But the log base b of b to the y says, what power of b equals b to the y? Well, y, right? B to the y equals b to the y. Now, a bit of notation. Depending on the context of one's professional setting, A log without a base can indicate a base of 10. This is often seen in engineering. Or 2. This is often seen in electrical and computer engineering. Or base of e in most mathematical settings. Now, I happen to take this notation approach, that log without a base is log base e. Now, some people, for some inexplicable reason, will write log base 10, log base 2, but when it comes to log base e, suddenly we become French, and we write ln for log base e, which is short for the French logarithme naturel, forgive my French, or possibly it's short for the Latin logarithmus naturali, forgive my Latin. Now, why any other base? We keep it in English and put a subscript. But for base E, all of a sudden we speak a different language. It's strange, and I don't want any part of it. If you want to write ln, that's your business. But for the rest of these notes, a log without a base is a natural log, or a base E. So, let's use the chain rule to compute the derivative of g of x equals b to the x for some positive b. Now, we know that b equals e to the log b. Therefore, g of x equals e to the log b to the x. The chain rule says g prime of x is, well, the derivative of e to something is e to something, and we're going to evaluate at log b of x. So I just get e to the log b of x times the derivative of log b times x. Now, log b is just a number. The derivative of a number times x is, well, that number. So I get e to the log b times x times log b. Now, of course, remember that e to the log b times x is b to the x. So the derivative of b to the x is b to the x times the natural logarithm of b. Now, that's important because it means that the derivative of every exponential function, right, with a positive base, has a derivative proportional to itself. Of course, if the base is e, then that constant of proportionality is 1, because the natural log of e is 1. The natural log of e says e raised to what number is e? Well, e raised to the number 1. All right, let's flex our chain rule on another example. We can use the chain rule to compute the derivative of the logarithm for any positive base. Remember that g composed with log b of x equals x. Therefore, the derivative of g composed of log b of x equals the derivative of x, which is 1. Now, if I apply the chain rule to the derivative of the composition on the left, I get g prime of log b of x times the derivative of log b of x. Solving for the derivative of log b of x, I get 1 over g prime of log b of x. Now I know what g prime is. G prime of x is b to the x times log b. So I'm going to evaluate g to the prime at log b of x. So I get b to the log b of x times log b. Right? That's the evaluation of g prime evaluated at log b of x. Now, by the way, b to the log b of x, right? Log b of x says b raised to what power is x? Well, b raised to that power is x. So I get 1 over x times the natural logarithm of b. In particular, if the base is e, then the derivative of the natural log is 1 over x, because the natural log of e is, again, 1. That's it for today.